Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Today we are going to learn about predicate logic. We know already the propositional logic. We'll see what are the limitations of propositional logic and how the predicate logic came and why it is important to learn the predicate logic. In today's class, we will see about the predicate logic introduction and some of the examples and why the predicate logic. Okay, so before learning about the predicate logic, first we will see what are the limitations of propositional logic. In the propositional logic, to draw the conclusions, we don't know the similarities of between the symbols. If our similarities are there, but we can't draw that conclusions. For example, here representing the facts about individuals, John, Paul, Peter. These three are the boys, but we don't have any type of symbols to represent John is a boy, Paul is a boy, and Peter is a boy. We have to represent with the A, comma, B, comma, C, like that only. With the relationships also to represent, there is no such kind of symbols in the propositional logic. And also, if you want to compute the n atoms in the expression, then you need to evaluate 2 to the power of n interpretations to know whether it is a tautology or it is a validity or it is a satisfiability. So this one is somewhat the larger truth table we need to compute. That's why there is a logic says that predicate logic, that is it is the logical extension of a propositional logic. Mainly it is focuses on validity, satisfiability and unsatisfiability. We'll see the definitions later. So here the predicate logic having the ability to represent facts using predicate statements. In the propositional logic, there is no such type of symbols to represent individuals. Like says that boy, John is a boy, Paul is a boy, and Peter is a boy. And if you want to say all birds can fly, so there is no such type of symbols to represent the entire statement. So here in the predicate logic, we can draw the conclusion says that boy John, boy Paul, boy Peter. If you want to represent the three at a time also, you can write a boy of X. X is a value which will be bounded with the actual value. X is a variable which can be bounded with the actual value. X is a John, X is a Paul, X is a Peter. Okay, let's see what are the predicate statements. The statements containing the predicates and variables. In the previous example, boy of John, boy of Paul. The boy is a relationship or property and John is a variable. The boy is called as the predicate or a relationship. Let's see here. Example, boy of X. X is the variable and boy represent as the boy is a predicate or relationship. Predicate or relationship. X is a variable representing individuals like a John, Paul and Mike. Okay, so the predicate symbols and argument, the same definition. Predicate symbol represent a property or relationship and its argument specifies the entity. Boy is a predicate symbol and X is its argument representing the individuals, which means Paul, John and Peter. Next, let's see how to assign the truth values in the predicate logic. In the predicate statements become either true or false like a propositional logic when variables are bounded to actual value. We can't write a boy of X equal to true because we don't know whether X is a boy or girl. So it needs to bound its actual value, then only we can assign the true or false values to its predicate statement. So look at here, boy of Peter equal to true, boy of Mary equal to false because Mary is a girl. And what are the advantages of predicate logic over propositional logic? Already we have discussed that limitations. So the first one, representing statements like all birds fly. So this statement we can't represent in the propositional logic. And removal of limitations. So to represent individuals, there is no such type of symbols in the propositional logic. And one more is, if you want to compute the expression, for example, n atoms are there in the expression, then you supposed to compute 2 to the power of n atoms. Then only you can find out whether that expression is valid or satisfiable or unsatisfiable. Let's see what is a predicate calculus. So transforming into predicate logic by adding inference rules. So here there are 3 more logical notations in the addition to propositional logic. Whatever there in the propositional logic connectivity symbols, all those are present in this predicate logic also. But addition to this propositional logic connectivities, we are having 3 more notations. Let's see. The first one is a term. A term refers to a variable or constant or n-place function. A function is a mapping takes n terms as input and returns into a single term, written as a function of t1 to tn, where t1 and tn are the terms. Okay, so here we can take x comma y comma z, like that. All these are the variables, or we can say in some scenarios it is a constant. Okay, term is nothing but a variable. Remember in such a way. Next one is a predicate. The predicate is a relation that maps n terms to a truth value. So it is the predicate is a relation or property of that particular variable. Okay, either which is a true or false. Next, the third notation is quantifiers. Additionally, in this too, here this is the most important one. Quantifiers are used with the variables and come in 2 forms. The first one is for all, and second one is their existing. These are the universal quantifiers, for all and their exist. So we can denote the variables by uppercase letters, and the functions or predicate values are derived represented with the smaller case letters. Let's see the example. The constants are represented with the 6, 10, like that, and the variables are represented with the John. John is a actual value. Okay, functions on the other hand may be represented by lowercase letters such as f of x, g of x, like that. We can define the functions. So let's see the well-formed formulas. In these well-formed formulas, if you take alpha and beta are the 2 well-formed formulas, and these 5 also well-formed formulas. Negation alpha, alpha or beta, alpha and beta, alpha implies beta, alpha equivalents beta, also well-formed formulas. Next, if alpha is a well-formed formula and x is a free variable in alpha, then for all x alpha and there exists x alpha are also well-formed formula. For example, here alpha is a well-formed formula and x is a free variable. Then for all x alpha is also well-formed formula. There exists x alpha is also well-formed formula. Along with that 5 well-formed formulas, we are having these 2 also. So here well-formed formula can be built by applying some of the rules. Let's see here how it will be indicated, how it will be represented in the predicate logic. If a statement x is a brother of y can be easily represented in the predicate calculus. So we can write brother is a relationship and x is a brother of y. So we can write brother is a predicate, x comma y. Then how we can read x is a brother of y. Next, let's see another function example. A statement that Peter loves his son. Then how we will write love is a predicate, love Peter comma son Peter. Okay, here son is the function, so love is the predicate and Peter loves Peter's son. Okay, look at here. A statement that Peter loves his son is represented as love Peter comma son of Peter. Son is a function. Let's see another example. A statement that every human is a mortal. How it will be represented in the predicate logic. So let us represent the statement X is a human, then human of X. Means it is a variable. It is not bounded with the actual value. And X is a mortal as mortal of X. So the corresponding value is every human is a mortal. Then for all X, human of X implies to the mortal of X. Let's see the next one. First order predicate calculus. What is meant by first order predicate calculus? If the quantification in predicate formula is only on simple variables, for example, for all X, P of X, then it is a simple first order predicate logic. When the quantifiers applied to the simple variables, then it is called as first order predicate calculus. When we apply the quantifiers on the functions, then it is called as the second order predicate calculus or logic. We will see the in the next classes. In this session, we will see the first order predicate. Let's look at the definition. If the quantification in predicate formula is only on simple variables and not on the predicate or functions, then it is called first order predicate calculus. If the quantification is over first order predicates, means on the functions, then it becomes second order predicate calculus. Let's see the example. For all P, P is a function, so it is a second order predicate statement. Whereas for all X, for all Y, P of X equivalents P of Y, then it is a first order predicate statement. The quantification is applied on the variables, not on the functions. If you see this formula, this example, the for all is a quantifier which is applied on the P. P is a function, so it is a second order predicate. So let's see the next one. The first order predicate calculus is a formal language which is a wide variety of statements will be expressed. So here we'll see the rules. The rules are similar to those used in propositional calculus. Those are same. When inference rules are added to the first order predicate calculus, then it becomes to the first order predicate logic. In short, we can call it as FOL. Using inference rules, one can derive new formulas. Means based on the existing rules, we can derive the new formula. Let's see the next, how to interpretations of the formula in FOL, first order predicate logic. So in propositional logic, an interpretation simply refers to an assignment of truth or false values to an atom. So since variables are involved in FOL, we need to do more than a simple assignment of values. Okay, so in a propositional logic, we'll assign A equal to true, B equal to false. That's it. There is nothing to do. Based upon the already we have 5 connectivities. If A equal to true means negation of A equal to false. There are 5 truth tables are there. Based upon those values, we will interpret all the rows and columns values to find out whether it is valid or satisfied. So, but in this case of first order predicate logic, it is not enough to assign the values. We need to interpret. An interpretation of a formula alpha in FOL is not just restricted to assigning the truth values. It consists of a non-empty domain D. The domain data, whatever there, we need to consider the domain D, and involves assignment of values to each constant, function symbols, and also an assignment of truth values. So in addition to the assigning the truth values, we are having the domain values and also constants. So each formula alpha is evaluated to be true or false under given interpretation I over a given domain D. Based upon the domain D, we have to interpret. Let's see the example. So here for all x p of x equal to true, if and only if p of x equal to true and x belongs to D. Otherwise it is false. It should be available in the domain D. There exists x p of x equal to true if and only if there exists C belongs to D such that P of C equal to true, otherwise it is false. Let's see evaluate the truth value of an FOL formula for all x there exists y, P of x comma y under the following interpretation. So let's see the example here. The domain D equal to 1 comma 2, P of 1 comma 1 equal to false, P of 1 comma 2 equal to true, P of 2 comma 1 equal to true, P of 2 comma 2 equal to false. So we need to interpret whether the alpha is a true or false. Let's check. So for all x, if x equal to 1, then there exists y, P of 1 comma 2. What is P of 1 comma 2? True. Next, x equal to 2. P of 2 comma 1 equal to true. Here we need to check there exists first 2 belongs to D or not. Yes, 2 belongs to D, and there exists 1 belongs to D or not. Yes, there exists 1 belongs to D. So under the interpretation I, where x equal to 1, it is true. Under the interpretation of x equal to 2, it is also true. Let's see. P of 1 comma 2 is true. P of 2 comma 1 equal to true. So here we'll conclude that alpha is true under interpretation I. How we derived this? Based upon the formula. Here first we have taken x equal to 1. If x equal to 1 means y equal to 2. So for all x, there exists y belongs to D or not. We need to check. If it is S, then we need to substitute the values in the function P of x comma y. P of 1 comma 2 where x equal to 1, y equal to 2. Then we need to check whether the value assigned is true or false. Yes, it is P of 1 comma 2 is true. Then the second interpretation where x equal to 2, y equal to 1. And before substituting the values into the function, first we need to check the whether there exists y belongs to D or not. Yes, it is. Then we need to substitute the values and find out whether it is assigned a true or false. In the two interpretations, it is a true. So we can conclude that alpha is true under interpretation I. Let's see what are the definitions of satisfiability and unsatisfiability. Okay. So here a formula alpha is said to be satisfiable if and only if there exists an interpretation I such that alpha is evaluated to be true under I. And we can say that I is a model of alpha or I satisfies alpha. So it needs to be interpreted to be true, then only we can say satisfied. Then a formula alpha is said to be unsatisfiable if and only if there exists no interpretation that satisfies alpha. So there is no model to satisfy the alpha. Next, formula alpha is said to be valid if and only if for every interpretation I, alpha is true. Even one is true, then it is satisfied. There is no interpretation says that true, then it is unsatisfiable. If all the interpretations are true, then it is valid. A formula alpha is called logical consequence of a set of formulae alpha 1 to alpha n if and only if for every interpretation I, if alpha 1 and alpha 2 and so on alpha n is evaluated to be true, then alpha is also to be true. When this formula is true, then when applying the AND connectivity, then automatically alpha is true. In this predicate logic, we will have two types of forms. The first one is a Prenex normal form or PNF, and second one is a Skolemization form. The PNF form is nothing but when the formula alpha contains each variable in the formula having the quantifier q, then it is says that it is in the form of PNF. Let's see the definition. A closed formula alpha in FOL is said to be in PNF if and only if alpha is represented as Q1x, Q1, X1, Q2, X2 and so on, Q1, Xn, M. So this Q1, X1, Q2, X2 and so on, Q1, Xn is called as premix, and M is called as matrix, and here Q is nothing but quantifier. Q is nothing but for all are there exist, and X1, X2 and so on, Xn are the variables. So the list of quantifiers is called prefix, and M is called as the matrix of a formula alpha. So let's see the example here. For example, there exists X for all Y, P of X or Q of X comma Y is in PNF notation, because here we are having two variables. For two variables, there are quantifiers. There exists X for all Y. Then it says that it is in the PNF premix normal form. The next example, whereas for all X, P of X implies there exists X, Q of X comma Y. So here how many variables? Two variables are there, X comma Y. But the quantifiers applied to only on the X, not to on the Y. So it is not in the form of PNF. How many variables are there? For those variables, for each and every variable, the quantification is required. Then only that formula is in the form of PNF. Otherwise, it is not in the PNF notation. Let's see the conversion of formula into PNF notation. A formula can be easily transformed or converted into PNF using various equivalence laws. Already we have seen so many equivalence laws in the propositional logic. So additional in that, some of the conventions that will be used to understand this concept is alpha without variable, alpha with it contains a variable, the quantifier. Let's see the equivalence laws. The first one, this asterisk represents and are symbols. Based upon the rule, we can eliminate that one. For example, look at here, Q of X, alpha X or beta. Then we can take Q of X separately and alpha of X or beta of X. This asterisk symbol represent the both based upon the formula. So let's see the law one. First one, the quantifier X, alpha X asterisk beta equivalent to, take out of the quantification out of the formula and alpha X into beta. Similarly here also alpha into Q of X in beta X, then take this quantifier X out of this formula, then Q of X alpha into beta of X is equivalent to this one. Next, let's see the negation. Negation of for all X into alpha X, then it is there exists X negation of alpha X is equivalent that. Negation of there exists X alpha X equivalent to for all X negation of alpha X. Both are similar, vice versa. Next, let's prove this one. Negation of alpha X, negation of there exists X alpha X is equivalent to for all X negation of alpha X. So the IBNE interpretation over a domain D. To prove the equivalence law, this one we have to prove first this one is true. Then if and only if the for all X negation of alpha X is true under any interpretation I over domain D. So let us assume there exists negation of there exists X alpha X is true under interpretation I domain D, and prove that this one is also true. So here this one is assumption, then automatically it implies that that second one is true. Let's see here. For all X, alpha X is false. That is for all X, negation of alpha X is true. If you take X is true, the negation of X is false. Here for all X, alpha X is false. The negation of alpha X is true. So the next laws are the law 5 and law 6 for all X, alpha X and for all X, beta X. Then take this quantification alpha X and beta X and there exists X also similar one. But it is not vice versa. It is only for all X and there exists R. Look at here. For all X, R symbol. It is not equivalent. There exists AND symbol. It is not equivalent. Only for all X AND symbol, there exists R symbol. Let's see one more example here, showing that it is not equivalent under the interpretation. So here there exists X, P of X, and there exists X, Q of X. So here when X equal to 1, there exists X, P of X. What is the P of X? 1 is true, and there exists X, Q of X. What is Q of X? Q of X equal to false. True and false, false. So here the formula is false under interpretation I. Therefore, we can conclude that this is not equivalent. There exists X, P of X. When X equal to 1, then P of 1. What is P of 1 here? True. Next, there exists X, Q of X. What is Q of 1? Q of 1 equal to false. Then the truth table. True and false is false. Let's see the next form, that is a standard form or scolomization form. In the previous one, PNF form, for each and every variable will have quantifier, but in the scolomization, let's see the definition. The Predicate normal form of a given formula can be further transformed into a special form called scolomization or standard form. This form provides clauses which can then be used as a resolution process. The process of eliminating quantifiers from the prefix of a PNF notation and replacing the corresponding variable by a constant or a function is called a scolomization. Scolom constant or scolom function. Let's see the scolomization procedure. So here this is in the form of PNF. We need to convert into the scolomization or standard form. So the step that need to be followed in the scolomization procedure is, first we need to scan prefix from left to right. If the quantifier is in the first one, if Q1 is the first existential quantifier, then choose a new constant. C not belongs to, that constant is not belongs to the set of constant in M matrix. Replace all occurrences of x1 appearing in matrix M by C and delete Q1 x1 from the prefix to obtain the new prefix form. If QR is the last existential quantifier, then replace that QR minus 1 with the R minus 1 that is not belongs to the set of functions appearing in M. Replace all occurrences of XR in M by f of x1 to xr minus 1. Then remove qr and xr. If it is the first one, then it will be replaced with the constant. If it is the function, then it will be replaced with the other function that is not belongs to the already having the functions. Repeating the same procedure till all existential quantifiers are removed from M. Let's see some of the predicate statements. If they have given Marcus was a man, then we can write man is a predicate and Marcus is a variable. Marcus was a Pompeian, then Pompeian is a predicate and Marcus is a variable. Marcus was born in 40 AD, then born is the predicate, Marcus, 40. Marcus born in 40 AD. We can read out like that. All men are mortal. Then for all x, men of x, mortal of x, implied that. All Pompeians died when the volcano erupted in 79 AD. Then erupted volcano, 79, and for all x, Pompeian x belongs to died x, 79. In such a way, we have to write the predicate statements. In today, we have seen what are the limitations of propositional logic, propositional logic, and we have seen the predicate logic, how to symbolize the statement in predicate logic, and we have seen the equivalence laws, and we have seen the two forms. One is PNF, another one is columnization or standard normal form. And we have seen some examples how to interpret and how to derive the validity, satisfiability and unsatisfiability of a given formula alpha. Thank you.